Good morning, good afternoon, good evening, everyone, and welcome to our webinar. So thank you so much for joining us today. If you're watching, hopefully you have heard about our recent release of the new Embodied Carbon tool within EDGE certification. And we'll just spend a few minutes starting off this webinar with some housekeeping. So my name is Michelle Farrell. I'm a Senior Operations Officer at IFC, and I'll be serving as your MC today. And I'll call on the speakers to contribute their details to our webinar. So now here is the first in many of our webinars that we have that talk about the new capabilities of EDGE and also the science behind those capabilities. Now, all of our webinars are recorded, and the presentations and recording will be available after the session. Another thing that's very important is a survey. So this is going to follow our webinar today, and we would greatly appreciate if you would contribute to this. Now, during our webinar, you may use the chat function to ask questions in the WebEx application, and we will address as many of these as possible at the end of the session. So today we have an exciting agenda, and we're going to look at these 4 different key categories. So first, what is embodied carbon and how are these capabilities now available inside of EDGE? Next, we're going to talk about an overview of embodied carbon in general and how that affects our construction materials and buildings and the building footprint of our structures. Then we're going to talk about some global trends around embodied carbon. And finally, we're going to address audience questions. So before we get started, what we want to talk about is really that 11%. What comes from the manufacturing of building materials and products, such as steel, cement, and glass. Now, to decarbonize the building materials sector, all stakeholders need to understand the environmental impact of their decisions regarding material selections during the life cycle. Now, doing so requires getting the right data to the right stakeholders at the times of decision making. So now, building environment carbon rating systems need to include better rewards for avoiding new construction when possible and shifting to low carbon or bio-based solutions. Now, to get the right information to the right stakeholders at the exact right time, we need to have a better systems thinking when it comes to designing resource efficient buildings. Now, when we look at what the global ABC says, they really stress that materials must be selected based on not just their operational impact, but their life cycle impact. Another thing is this must be done early in the design process. And then codes must account for embodied carbon. But how do we get this information to us at this early design process? And that's one of the key questions that we're going to address today with putting embodied carbon inside of EDGE. So allow me to hand over and explain this change to Ommid Saberi. Now, Ommid is based in Washington, D.C., and is the global technical lead for the EDGE Green Building Certification Program and the global lead for BRI, the Building Resilience Index. Now, Ommid works across projects at the World Bank Group, including IFC's investment and advisory branches, and has done extensive work within the property sector, as well as funds and commercial banks to divert investments to climate smart and resilience projects. So please let me pass it over to you, Ommid.
Thank you so much, Michelle, and I'm very pleased to have our distinguished guests here. And we are also extremely excited to see so much requests from the market and so much attention from the market to this subject, which is extremely important for us at IFC and World Bank. The brief mention here, I wouldn't take too much time because I want to hear and learn more from our guests here. But what I'd like to briefly mention is that financial institutions are key for this transition in the materials of the buildings. we are seeing that more and more by reducing the operational energy in buildings, materials are becoming more and more important. But the importance of the materials can be only addressed if we come up with solutions that drives demand for the supply chain. The supply chain is ready to shift toward lower carbon materials. On the other hand, we have builders and buildings that are certifying their buildings. We have projects in 120 countries that are certifying projects. However, the linkage between the construction sector and the materials providers has been difficult because calculating embodied carbon or life cycle costing has been very complicated. Is quite well developed in Europe, but when you go outside Europe to Latin America, to Africa or Asia, you can see that there is a lot of knowledge gap. So what we have been doing is trying to come up with a solution that is easy to adopt and for the designers to be able to design their assets with low carbon solutions, but then also for the suppliers to be able to use their data input to the system and connect the materials embodied carbon to actual buildings conditions. We have been working with Global Alliance for Building and Construction. We have been also supporting different programs around the world for decarbonizing building sector. And the key we find is that if we can bring the financial sector, such as international finance organizations, EIB, EBRD, and others, to all we play the same song and together try to move the market towards decarbonization, that would be a faster transition towards decarbonized supply chain. The EDGE program has started 10 years ago, and in the last 10 years, the program has evolved quite a lot. And introducing embodied carbon has been one of our biggest changes towards enabling supply chain to decarbonize. I'm also here to welcome Professor Karen to speak about the experience from Europe, and Dr. Martin as well to talk about the work that has been happening on his side, on his research. And then finally, my colleague Irene would be explaining more details of how the EDGE program would include the embodied carbon in more detail. Back to you, Michelle, and thank you for joining us. Michelle, you're on mute.
We cannot hear you, Michelle.
Got stuck for a second. All right, so our next speaker is Professor Scrivener. So Professor Karen has been working with the Swiss Federal Institute for Technology, and she has been working on cement and concrete for 40 years. Her career, moving from academia to industry and back, gives her extremely unique insights on both the scientific fundamentals and practical realities of materials. Her main focus is on lowering CO2 emissions from the built environment. And this has led her to the development of many different types of products, which can cut CO2 emissions by up to 40%, including a type of LC3 cement. Through her roles in journal editing and leading think groups on sustainability, she has truly become one of the most influential people in this field. So please, Professor, let me hand the stage over to you.
Okay, thank you very much, Michelle. And I'll try to share the screen. Right, okay. So do you see this okay? Okay.
Yes. Yeah.
So I'm very honored at the opportunity to speak in this webinar. And in this presentation, I'm going to try to explain what is embodied CO2, and particularly why this is not the same thing as embodied energy. Now, before I start, I want to emphasize the importance of embodied carbon, because this is this comes at the beginning. When you build a structure or a building, the embodied CO2 is already there. And once it's done, you can't do much about it. And this is in contrast to operational energy, which emerges through the life of a building, but also is something that can be improved through upgrades and improvements in building efficiency. And we know now that from the point of view of climate change, what is very important is to act fast. It's much more important, the emissions we're going to be emitting in the next decade than after 2050. So in this context, embodied CO2 becomes very important. Now, in a nutshell, the reason that we have to look embodied CO2 rather than just embodied energy is that the two most used construction materials, that's to say cement in the form of concrete and steel, have a considerable amount of their emissions which are not energy related. And these are often called process emissions. So if we look at the case of cement, the first stage in producing cement is producing what we call clinker. This is the material that comes out of this very big cement kiln you see on the left here. And a lot of people talk about the very high temperatures needed to produce clinker. But even though we have these high temperatures, only a minority of the emissions, about 40%, are coming from the fuel. And this process is already highly optimized. There is unlikely to be much further improvement there. And most importantly, now we can use a lot of waste fuels, so we can avoid, to a very large extent, the use of fossil fuels. What is much more important is the 60% of emissions, which is coming from the breakdown of calcium carbonate. So calcium carbonate is limestone, and limestone is 60% of the raw material to produce cement. And during the production, this first of all breaks down into calcium oxide and CO2. And this simple chemical reaction accounts for about 60% of emissions. So for producing clinker, we have an average CO2 of about 850 kilograms per ton, and of that, about 510 is coming from this process emission. Now, these emissions from clinker are very important because as then we move from the clinker step to the cement step, we add in other ingredients to make it cement. And then, of course, we use the cement to make concrete. Even though in the final concrete, the clinker may only make up about 10%, this still accounts for about 90% of the CO2 emissions. Now, it's not so well known, but actually it's a similar story when we look at steel, because when we produce steel, we start with iron ore. So iron ore is iron oxide. And even though people think that the carbon we add is mostly fuel, this is not in fact true, because a lot of that carbon is used to take the oxygen from the iron, so that we go from iron oxide plus carbon to iron plus CO2. And this accounts for about 600 kilograms per ton of iron produced. And then in addition, because we have this thing which is called flux, which also uses limestone and magnesium carbonate, this produces even more processed CO2. So altogether, we have about 730 kilograms of CO2 per ton from this process emission. So these two materials together make up a very, very important part of all the materials we use. Materials based on cement are overwhelmingly dominant. They make up about over 30 billion tons of material in the form of concrete and in the form of mortar. Steel is here, is also very important, and in between we have clay-fired bricks. Now, before going on, it's important to say something about timber, because timber is very controversial. A lot of people claim that this can really solve the problem. I don't want to get too much into that debate, because the problem is the figures for timber depend very much on the type of forestry the timber is coming from. The best figures come when you have sustainable forestry, and that's not all forestry. But even apart from that controversy on the figures, the problem is the amount. That the amount of timber we're producing today is really very small compared to all those other materials, steel, bricks, and cementitious. It's way less than 5%. And it's not really possible to increase that in any meaningful way. So, of course, if we have timber available, it's a very nice material. We should use it, but we have to accept that we simply don't have enough material available. And this recent report from the World Resources Institute goes into those problems in more detail. But just to give you one figure from another report, if we wanted to replace just 1/4 of concrete with timber, we would have to plant new sustainable forests 1.5 times the size of India. And of course, this would be great. We need to plant more trees, but we have to think about the practicality of that. Now, concrete gets this very bad name, but from an intrinsic point of view, it's actually a material with some of the lowest embodied CO2 and embodied energy there is, as seen in this graph here. It's only because we use so much of it that this all adds up to this very important amount of CO2 emissions of about 8% of world emissions. And if we look on the whole building level, which Martin will talk in more detail about after me, we see that if we have different types of structure of material, then we don't have all that much difference in the overall building amount in terms of CO2 per meter squared. But particularly in the concrete case, we have tremendous dispersion. And there are some good reasons for this. Of course, you don't have to use more concrete in a high-rise building than you do in a low-rise building. But it also highlights the fact that there's considerable room for improvement. And this is really what we need to focus on, the tremendous potential for improvement. To look at another thing, and I think Martin again will go into this, we have to look at the different types of material, and about 50% of the embodied CO2 is coming from the structure. The rest is coming from the envelope and the interior. And it's often the structure where we have the most chance to make changes. So the conclusion of all of this is, cement and concrete and steel cannot easily be replaced, but they can be used more efficiently. So, for example, for concrete, we need to look through all these different stages, through the stage of the production of clinker I explained earlier, but then reduce the amount of clinker we put in cements by using other materials, which are called SCMs, which stands for supplementary cementitious materials, but then go on to reduce the cement in the concrete, which can be done through good aggregate grading and use of admixtures, and then think about using the concrete efficiently in the buildings, and of course, really considering whether we need to use new buildings or whether we can reuse buildings or recycle. And this report we produced in 2017 indicated that we could achieve reductions of about 80% in this way. And very nicely, this much more recent publication had made a much more detailed calculation, which comes up with the figure of 76% possible with these strategies. So this really indicates what a tremendous amount can be done with technologies we have available today. Now, to look at the first stage, which is reducing the clinker factor. Traditionally, we used to take clinker and gypsum, and these used to be ground together to produce cement. Nowadays, this is only a very small minority of cement, and most cements contain additional materials such as limestone, such as fly ash, which comes from burning coal to produce electricity, and slag, which comes from producing iron. Now, these two materials, fly ash and slag, come from very CO2 intensive processes themselves. And of course, burning coal to produce electricity is the number one thing we need to avoid in order to reduce CO2 emissions. So we need to look to new replacement materials such as calcined clay. And it's also a question of availability, because even today, the amount of slag and fly ash we have available are quite small in proportion to the amount of cement we use. Slag, for example, only makes up about 8% of our demand for cement, and something like 95% of this is already used. So there's little further potential for CO2 reduction. But if we go to this new material, well, it's not new. In fact, it has been used for over 100 years, but it hasn't been as used as it should be. If we take clays, which can be calcined, and we mix them with limestone, we can come up with this new cement, which we call LC3, which makes a coupled substitution together of calcined clay and limestone. And it's this LC3 which has the potential to reduce emissions by up to 40% compared to no additions at all. And how can it do this? Well, we replace the clinker, and we saw early on that most of the CO2 emissions are coming from the clinker. We replace this by a combination of calcined clay and limestone. There are some emissions from calcining the clay, but much, much less than from clinker, generally less than 1/4. And limestone has virtually no emissions at all when it's not heated up. And with this combination, we can have comparable strength to ordinary Portland cement. This can be used throughout the whole range of materials. So we have 50% less clinker, up to 40% less CO2, similar strength, better chloride resistance, better resistance to alkali silica reaction, etc. The kind of clays which are suitable for this are very widely available. Everywhere we have this kind of orangey color. We have clays that can be suitable. And this is in contrast to limestone, which is the first raw material, which in fact is difficult to find in some parts of Africa, which have to import clinker. So this can be a very good solution, particularly because in the next 30 years from now till 2050, we're going to see a huge shift in the use of cement away from China, which has been the dominant source of growth for the last 30 years, towards India, Latin America, and particularly Africa. So the potential from bringing in calcined clay as a substitute material is really enormous. This graph here shows the average levels of substitution today, and that this hasn't really progressed in the last 10 years because of the limitation in the availability of slag and fly ash. Now, if we remove that by bringing calcined clay into the mix, we easily can go to substitution levels of about 40%, which would represent a saving of about 400 million tons of CO2 compared to business as usual. If we're looking further ahead towards 2050, we can advance technically to use higher levels of substitution, and I think we can aim at saving at least 800 million tons of CO2 per year. And the good news is that we can actually do this while saving cost. So LC3 is a solution that can be produced more cheaply than the reference ordinary Portland cement. So going back to this chain of things and emphasizing the LC3 as the first step, we then need to think about cementing concrete. And if we look at the figures from the literature, we see that there's this huge spread. So to get exactly the same strength, we have some concretes which are using this amount of binder and some concretes which are right up here. That's to say using 4 times as much cement as needed. And 4 times as much cement as needed is equivalent to 4 times as much CO2. And one way we can reduce this dispersion is by going to away from site mixing to modern methods of industrial production like ready mix, and certainly not going to things like 3D printing, which is taking us in the opposite direction. We need to use cement more efficiently in concrete. This graph here shows real figures from environmental product declarations in Europe and North America, which again shows the dispersion of the products on the market. And while Europe seems to be doing better, you can see there's a limit here. And this limit is because the code in Europe specifies a minimum cement concrete, which is an outdated specification that really needs to be reconsidered. So to quickly finish with 2 practical examples to show what we can do, first of all, we compared LC3 concrete with concretes prescribed in Dubai. So these were designed to be durable concretes, which contained a considerable proportion of slag, and for the high strength option of silica fume. And first of all, we replaced the binder by LC3, and then we optimized the binder. And what we can see here is, first of all, we managed to contain strengths which were much more in line with the specification. And that's important because you don't really want higher strength, because if you have higher strength than specified, then your reinforcement design can be wrong. But here on the right, we see the CO2 savings. And we see systematically CO2 savings possible of around 20–25% by optimizing your concrete. Now, this is a high-tech application going to concrete strengths of about 80 megapascals, but we can have the same thing when we go to building blocks. And building blocks are a commonly used material throughout the world. And here we can see a study we did where we compared the LCA from fireclay bricks, from earth bricks blocks, and from concrete blocks. And first of all, in contrast to what many people believe, when you have earth blocks which are stabilized by cement, they're not necessarily more efficient than concrete blocks. Concrete blocks are in fact more efficient. And we can make those concrete blocks more efficient still by using this LC3 binder. So those are just 2 examples which really highlight how there's considerable room for progress in building materials while ending up with a product that's basically the same, like people can use. And we can go further when we look at concrete in buildings. At the structural level, we have to develop tools which make it easier to calculate and compare possibilities. And this just shows you some of the 1,000 different possibilities of a building, which all comply with the codes. And you see the tremendous variation in terms of the embodied CO2 per meter squared of building in these different possibilities. So with this, we see here these possibility to combine all these effects. And these first ones I've talked about, more efficient design and construction, more efficient production of concrete, savings in concrete and binders. These are all solutions which can potentially save money. And as I said, we potentially have savings of up to 80% through these different possibilities. At the end of the day, we have to have some measure of carbon capture and storage, but this is where we have a totally different price, much, much more expensive, and much more complicated. This was the pipe network that's deemed to be necessary just in Europe to efficiently capture all the CO2 from industrial production. And this will take time, and that's the problem. We don't have time, we have to move fast. So embodied CO2 is important. It mostly comes up front. It's not the same as embodied energy. And with the two most used materials, concrete and steel, cannot easily be replaced. But they can be used much more efficiently. And we need to do this more efficient use at all the possible levels, replacing clinker by supplementary cementitious materials, particularly clays, minimizing cement in concrete, and making good choices in design. And with that, I'd like to thank you for your attention. I'd like to excuse my voice, which I had a bad cold this week, which is why I'm not speaking very well. And I'll try to hand back to Michelle, if I can find out how to stop sharing.
Great, thank you so much, Karen. There we go.
Okay.
So now I would like to introduce Dr. Martin Röck, who is a research associate at KU Leuven, and he's also the founder and director of RSC Sustainability Consulting in Vienna and a co-founder of the Austrian Architects Collective. So Martin's work focuses on analyzing and mitigating climate and environmental impacts across the building life cycle to enable regenerative development of large-scale systems. So please, Martin, I'll pass it over to you.
Thank you very much, Michelle. So 1 second. So you should see my screen, is that correct?
Yes.
Perfect.
Looks good, thank you.
Thanks so much for the invitation to present here in this webinar. It's a real honor. It's also an honor to kind of speak after Professor Scrivener. I will elaborate more, as she already indicated, on the building level and speak a bit about the global trends and for embodied carbon in buildings, and also some insights on the building level regulation of whole life carbon, by example of Europe. First, I want to remind us about the context that we're working in. Karen Scrivener already mentioned it. This is a figure from the latest IPCC report, which just really shows that if we remain on the trajectory of currently implemented policies, which also include policies in the built environment and the construction sector, then we are really not on track to, in fact, reduce and limit warming to 2 degrees or 1.5 degrees. For this to happen, we need a lot more radical emission reductions than what currently is happening. So there's really an urgency of the climate emergency and a global decarbonization that is needed. And this also involves buildings and construction. As many of you will know, there are around 40% of the global energy-related emissions that relate directly to building, construction, and operation. And as Professor Scrivener just said, this figure is likely an underestimation because it does not consider certain process-related emissions. Reducing the whole life carbon of buildings is therefore very important for both building level as well as building stock level, so for building related emissions at the national and transnational and eventually global level. For this to happen, we really need to see comprehensive policy action to really enable this rapid emission reduction. And that's the kind of interface that my work also happens in at the science to policy interface. I really try to leverage the methods for life cycle assessment of buildings in a policy context to really inform decision making there. I want to give a quick recap what we talk about. Building LCA, life cycle assessment of buildings, is about spatial and temporal aspects. Spatial aspects mostly refer to products, processes that are happening within the building. So for example, we can have building materials which are being used within certain building sub-elements, within walls, within floors, and that eventually compose a full building. And what we do in building life cycle assessment is that we actually model building inventories. So we really try to capture the full picture of a building and all its parts and all its materials, including the processes that go into the building over its life cycle. And that's where the temporal dimension comes in, the life cycle or the time over years, over decades, when certain processes, when certain emissions occur. And that, as many of you will know, spans from raw material extraction over transport and production of a construction product, but it also includes the transport, the construction process. It includes several years, decades of building use, and it includes eventually an end-of-life stage, which also has several processes that are relevant. And the steps of calculating an LCA at building level is really mostly multiplication, starting from the activities, the products and processes which we put into the building, and the different scenarios or the different, again, activities that happen at different life cycle stages. So the first two give us the foreground inventory, as we call it, and then we multiply this with environmental indicators, with different methods for assessing the environmental impact of buildings, for example, to get the global warming potential or the climate impact of a building, or other life cycle assessment results. All of those results and all of those stages that lead up to the results are subject to an interpretation, and they come with a previous goal and scope definition. And as all LCA practitioners or people familiar with the procedure know, this is also a highly iterative process where you kind of have to go back sometimes to the goal and scope to really make sure that the result and the interpretation that you're making actually matches the assessment. And I also want to take a moment to clarify a term that Karen Scrivener already mentioned, emissions occurring upfront. What do we mean when we talk about upfront carbon? It's exactly these early stages of the product stage and of the construction stage, which together are the life cycle stage A, at least in the European standard, which is also used internationally. Then there is the use stage, embodied carbon, so that is maintenance, repair, replacement, or also refurbishment during the use stage of the building. And there is an end-of-life stage, deconstruction, transport, waste processing, and disposal, and some aspects related to reuse, recovery, or recycling, which usually end up in what we call Module D, because it is information that is to be reported separately and must not be combined with the other results. So all of this, A, B, C, is embodied carbon. And for the B stage, we also have operational carbon, which can be the emissions related to operational energy use or operational water use. So this is an important distinction, embodied carbon, operational carbon at the building level. And when I talk about whole life carbon, it really includes all of those, embodied and operational carbon from those different stages. Now I want to give you some insights into the crucial role of embodied carbon in the building life cycle. We already heard the embodied carbon perspective on different construction materials. Now I want to tell you why we think that it's really the hidden challenge for buildings, for new buildings in particular. And these results are based on a study that we did analyzing more than 650 building life cycle assessment cases. And based on a global data set of both residential and office buildings, we could show that previously existing buildings had a very low share of embodied carbon. So the dark blue part that you see here is the embodied carbon. The light blue part is the operational carbon. Existing buildings had a rather low share of embodied carbon. And over time, as operational energy efficiency increased and the related operational carbon emissions decreased, we see a shift that is on one side in the relative contribution of embodied carbon, which is now approaching 50% of life cycle emissions over 50 years of a building life cycle. But also in absolute terms, we see that embodied carbon has increased, especially for new and new advanced buildings, compared to what we previously saw in the construction of existing buildings. So embodied carbon in new buildings really has a share of 50% or more of building life cycle emissions. They have increased both relative and absolute terms. And for new buildings, it's really difficult to meet life cycle related climate targets. Some countries do already have life cycle related climate targets for buildings in place. Switzerland, for example, is one of those countries where they have target values in place. Denmark even has regulation in place that new construction projects have to meet. And it's not just an issue that this shift is kind of happening, but it's really an issue particularly in context of climate change. Because for effective climate change mitigation, it's important to understand the temporal dynamics of embodied and operational carbon, which are very different in nature. While the embodied carbon occurs in spikes, so for example, if you see here again, the A stage occurs at a certain time, and then the B stage occurs again throughout the life cycle, but the C stage occurs only at the very end of life of the building. And in contrast, building operation is very continuous. If we plot this on a time axis, so on the horizontal axis, you can imagine time. We start in 2020 and we look until 2060, 2070, 50 years of a building life cycle, as I said. And on the vertical axis, we look at the emissions that happen over this life cycle. We see that at first we have this red line, which creates the embodied carbon spike. And that's really the most important thing that occurs in the beginning, because the blue line, the operational carbon, really only accumulates over time, continuously over the building service life. And it takes more than 35 years for new advanced buildings to actually break even, where embodied carbon and operational carbon break even. So this upfront embodied carbon spike, as it's called, really dominates this time frame until 2040, until 2050, which is so important for effective climate change mitigation. And it also reveals the importance of reducing embodied carbon invested for new buildings today, because that's really what makes the difference for current new construction decisions. And that's also the reason why increasingly whole life carbon is being addressed in building design codes and also in regulation. And I want to share with you some of the work and also recommendations that we have developed in the European context to support European climate policy on the embodied carbon of buildings. One study that Karen Scrivener already briefly showed was a study where we again collected data on the embodied carbon and the whole life carbon of buildings across Europe to get an understanding of what kind of benchmarks we could develop for different building types in different European countries. And one perspective is particularly important here. It makes a difference whether we look at the embodied carbon of buildings per square meter of the building. So for example, here, you see that we can distinguish different building types. Single family houses on average were around 600 kilograms per square meter. Multifamily houses were a bit higher. Also for office buildings or other non-residential buildings, we can develop benchmarks for the kilogram per square meter. What we can do in addition is we can develop benchmarks per capita, which is actually a very valuable perspective, because buildings usually serve the purpose of providing a certain function for people. So it's not necessarily just about the number of square meters, but it's more about the number of people that are being served by a certain building. And if we look at the embodied carbon emissions from that perspective, we see a very different picture. Here, the single family houses have a higher value than the multifamily houses, just because the building design tends to be more efficient in multifamily houses when it comes to the number of people being housed or inhabiting the buildings. And we can take a similar perspective, a similar per capita perspective also on other building types. And as Karen Scrivener showed before, we do see quite some dispersion for the buildings within different types of structures. We also see quite a dispersion within the buildings of different types of uses. So here again, we're plotting different residential and non-residential building types and the embodied carbon that we see across the full life cycle. And you see that there are certain trends. Some building types tend to have higher values, other building types tend to have lower values per square meter of building. But also within the building categories, within the use categories, within the typologies, we see that there is a high potential for reducing embodied carbon, namely through smart design choices, through material efficiency, and through good building organization and layout. So a lot of things that can be influenced by architects and engineers. What we also saw in this study is that even within Europe, which was mentioned before as one of the front runners in this context, the data availability on building LCA or on the embodied and whole life carbon of buildings is actually still rather limited. So we have some countries which are also within Europe at the forefront of providing this data, of using this data for national policy and regulation. But there are also several countries where we found very little data available so far. And it's also one of the aspects that is being addressed by current research projects in the European context to generate more data on building LCA, on the whole life carbon emissions of buildings, to support countries to actually regulate on this aspect. And what I also wanted to show from this benchmarking study is that indeed we can look at the contribution of different parts of the building. Before we saw the distinction between structure, envelope, and internal elements, I believe. And in this study, we had a more extended scope on the building. So we also looked at the contribution of the substructure below ground and also embodied carbon of technical services and appliances. And especially for services in new advanced buildings, we find that the HVAC systems can have a very, very relevant contribution at a similar order of magnitude than the structure in some cases. So that's also a thing to consider when designing new buildings. And again, we can look at the distribution across the different life cycle stages. So these are again the letters that you saw before: the production stage, the transport stage, the embodied carbon during the use stage. You see that there are these embodied carbon spikes. For the production, most of the emissions are due to production. Then there is a bit of transport and construction. Also during the use phase of a building, quite a substantial number of embodied carbon emissions can occur because you have replacement, because you have maintenance. And then again, at the end of life, we also see embodied carbon emissions happening. And it's different for different building types, different typologies, and different structural systems. And as a last section, I want to show you or give you some insights from our work in supporting the European Commission in developing a roadmap for reducing whole life carbon of buildings across Europe. And this deploys a data model that has been one of the outputs of my own research, where we work to get highly detailed building LCA data covering the material level as well as the building level, so really providing insights on the different contributions at different spatial levels, as well as the contribution at different temporal levels. So to not aggregate just for the whole life cycle or just the upfront carbon, but really look at emissions at the different life cycle stages and even at the point in time of a building, and also look at different indicators, look at the actual material flows within the building and also different environmental and non-environmental indicators. And to this purpose, we developed what we call the SLICE data model, which gives us highly detailed information on exactly those aspects: spatial attributes, temporal attributes, and also different indicators. And this approach has been used in a study that we are currently concluding for the European Commission, modeling the whole European building stock clustered into 4 main regions. We modeled the embodied carbon and the whole life carbon related to the existing building operation, the energy retrofit of buildings, the deconstruction and demolition of the existing building stock, as well as the new building construction that is happening in Europe currently, as well as the projection until 2050. We did this for different building types: single family, multifamily, and office buildings. We also considered different energy performance levels in different regions across Europe, and also different construction material use, different structural systems being used in different European regions. And we applied a set of low carbon solutions to really focus on the reduction of embodied carbon, especially in new construction. And the results of this are manifold. One of the results at the building level are that we could derive different benchmarks for different building types. Here I'm just showing the new buildings that we modeled for the 4 different regions in a standard and a more advanced energy performance. We could investigate the contribution of different building elements or of different building materials within those building archetypes, so within those representative buildings. And we could also look at aspects like embodied carbon payback. So for example, in the case of a renovation, if you have an existing building that requires an energy renovation to improve the energy performance, then you can actually compare the operational carbon of the existing building before renovation and the operational carbon performance after renovation. And in between, you will have had an embodied carbon investment, and you can check how many years it takes for an amortization of this embodied carbon. So the embodied carbon payback, as we call it. And as I said, we looked at this not just for the baseline year 2020, but we looked at projections until 2050. And we investigated three main carbon reduction strategies or carbon reduction solutions, which we grouped into aspects related to improving the system, so optimizing building design, optimizing construction practices and material production, which mostly faces technical boundaries. Then we looked at strategies relating to shift. So for example, the use of timber instead of concrete, as we heard before, or of other low carbon or bio-based materials, where we mostly face availability boundaries. So there are also issues with scaling. And we also looked at solutions relating to avoid strategies. So that, for example, could be sufficiency related strategies, making best use of the existing building stock, or also reducing the floor area in new buildings, reducing the floor area per capita, where we mostly face social boundaries. It was very interesting to do this analysis. Just to give you an idea, we investigated three scenarios. The one is the business as usual, where we see embodied carbon looks like it was mostly staying the same. It's actually slightly increasing because there is an increasing rate of renovation also in Europe that is expected under current policies. But what we see for operational carbon is that it's expected to really go down, because the projection is that indeed the operational energy production will be decarbonized in the coming years. So that already leads to quite a reduction in operational carbon. Overall, it's a downward trend, but it's by no means as rapid as we would need to see. If you remember the first slide that I showed, the kind of rapid carbon reduction, rapid emission reduction that we need to see is not yet here. So we investigated one scenario that is called tech build, which deploys all the improve and the shift strategies. And here it's important to point out that we looked at the potential of those strategies to reduce emissions, embodied carbon emissions at the building level, but we also looked at the potential of strategies to actually be scaled up, so at the potential market share of different strategies. And that's what, for many strategies, really made the difference, because there are just problems of scaling. While at the building level, they might look very interesting. If you look at it from a European or even a global perspective, some of the strategies are not very scalable, and that creates a problem if we rely on them too much. So if in the tech build scenario, we see a lot stronger reduction on the operational side on one hand, but we also see even an increase on the embodied carbon side, because in this scenario, we also had more renovation. So overall, it's a stronger reduction, but it's still not sufficient. So in the life build scenario, we also considered the improve, the shift, and the avoid strategies, which in practical terms meant that we would extend the service life of existing buildings, actually reduce the new construction rates and shift resources to the retrofit of existing buildings, and also apply some more strategies to take more of a sufficiency approach to buildings and to building use. And maybe as a last point, even in this study, which is, as I said, measure driven, so we kind of approached it from the available strategies and modeled how far we could get, where they could take us if we deploy those strategies at scale. We still found, and that's also what we're discussing with the Commission, that the set of strategies that we're currently investigating are not yet taking us to the kind of decarbonization levels that we would need to see for the European building stock. So the key takeaways. The embodied carbon is the hidden challenge for effective climate mitigation, as I showed in the very beginning. It's mostly due to the upfront embodied carbon spike and the fact that it takes more than 3 decades for embodied carbon and operational carbon to actually break even, at least for new, advanced, highly energy efficient buildings. However, many solutions are readily available to reduce embodied carbon and also to reduce whole life carbons, also to reduce operational carbon emissions. And those really need to be deployed. So from the European analysis, we see that more effort is required and that a holistic effort is required. We need to see higher renovation rates and renovation depths. So we really recommend deep energy retrofits as much as possible. Decarbonization of space heating is required, the deployment of low carbon material production at scale, as well as the circular cascading use of materials, and to maximize the use of existing buildings. All of those are relevant strategies in the European context. And here I just wanted to put again the three main strategies that we looked at. So improve, which relates to efficiency strategies, shift, which aims at consistency, producing different, as well as the avoid strategies, which relate to sufficiency, and there the target is to produce or use less. And we saw that for Europe, and I'm taking this here as an example of Global North countries and Global North building stocks. One of our recommendations to the Commission is really to consider a deliberate reduction of new construction to free up resources for the renovation of the existing building stock. While this will be very different for countries and communities in the Global South, where, of course, we need an optimized low-carbon construction to really provide the infrastructure needed to ensure the well-being of the society there. And with this, I want to thank you very much for your attention and again, call for us all to tackle embodied carbon now. I'm curious to hear the other speakers and the discussion at the end. Thanks a lot.
Great, thank you so much, Martin. So now moving on to our final speaker, we're going to explore some of the ways that you can do this now inside of EDGE. So let me introduce Irene Montserrat. So Irene is based in Washington, D.C. and is the technical specialist for EDGE Green Building Certification Program. So Irene is a mechanical engineer and she's done extensive work in the building sector. So please let me pass it over to you, Irene.
Thank you, Michelle. Can you hear me okay? Yes? Can you hear me?
Yes.
Yes, great, thank you. Okay. Okay, great. I want to thank to our panelists for this super interesting conversation. I know they already have, but I want to keep stressing the importance of addressing embodied carbon if we are to reach our global decarbonization goals. So according to the International Energy Agency data, the building sector contributes to almost 40% of the global energy-related emissions. Martin already showed this number as well. But over 1/3 of these emissions are from embodied carbon. So this large impact can be avoided or largely reduced if we plan properly. However, one of the main barriers that we have seen is the lack of information and data availability. That was the motivation of IFC to have as much information available as possible and to have it free of charge, so everyone can have access to it. In the past, EDGE was addressing materials efficiency using embodied energy as an indicator. But this concept was very difficult to grasp. Many manufacturers did not know how to document it, and it was not really telling the whole picture, as Professor Karen explained in detail. But also this indicator was not accounting for the geographical and technological difference in production process of building materials in different countries. So for example, while making a concrete block may take the same amount of energy in India or in Mexico or in Australia, the emissions associated are very, very different due to fuel sources, grid mixes, etc. So for this reason, the EDGE app has upgraded from assessing embodied energy of materials in a building to assessing embodied carbon. For those, just to give a little bit more information, for those attendees that are not that familiar with EDGE, in our tool, we look at 11 material efficiency measures that forms the building embodied energy and embodied carbon. So we assess the floor construction, the roof, well, in floor, also intermediate floor finishing, roof, wall construction, interior and exterior walls, windows, including glazing and frames, and finally insulation of roof, wall, and floor. So the app immediately will show a baseline. You can see the graph. This is the results that you see using the app. So the graph on the right side This baseline will depend on the building type that the user selects, like from a school, residential, office, etc. It also depends on local practices and other factors. So it is very easy for the user to identify the best opportunities for saving, for savings in terms of material efficiency, or how to choose the low hanging fruits. So each embodied carbon indicator is reported as global warming potential in kilograms of CO2 equivalent. This system boundary for the data sets is based on a standard EN 15804 that covers modules A1 to A3. So Martin already explained these different modules. So our approach for embodied carbon is A1 to A3, which is also known as cradle to gate. This includes the extraction and processing of raw materials, the use of energy in upstream transport and manufacturing, and also any processing of secondary material and energy used once this secondary material has been recovered from waste. So for example, if we have a material that has recycled content, we must account for the energy associated to reprocessing this component. So our database has a total of 615 components, 164 construction materials and assembly materials. And we are also now providing a regionalized approach to the data. As I mentioned earlier, the importance of having or distinguishing the processes in different countries or in different regions. So this analysis is refining based on global regions and the rate of import and export certain materials in those regions. So you can see on the right side the list of regions that we currently have. East Europe, West Europe, Middle East and Africa, Asia, Latin America, and the United States and Canada. So while the user selects one system on the Edge app, on the drop-down menu, they only select one system, such as concrete sandwich panel. The back-end calculations already take into consideration all the elements associated with this assembly, such as plaster, if there is content of steel, etc. So the user doesn't really have to worry on specifying one by one. The user only sees one element in the app. Like you can see, this is what the user will see, the list of elements depending on the module that is being assessed, the exterior walls, interior walls. As I explained, we have different levels. So another unique feature that was recently added to the tool is that now the user is able to add new customized materials or innovative materials and their embodied carbon values. So for example, if someone wants to add a concrete block with LC3, as mentioned by Professor Karen in her presentation, so now they are able to do so using our app. So the user can claim savings on embodied carbon from customized materials by verifying this material according to ISO 14067, or if they have the materials environmental product declaration EPD. So here on the screen you can see that once the user selects customized material, a new box will come that you can see on the right side, where the user is able to input some basic information about the material, the name, and more importantly, what's the embodied carbon of that material according to the standards that I already mentioned. So this is the end of my presentation. I would like to encourage our attendees to check our materials tab. Our tool that is free and available to everyone if you haven't done it yet. Thank you.
Okay, great. Thank you so much, Irene. So now we're going to dive into some questions. We have a lot of questions from the audience, so please forgive us if we don't get to everyone today. And okay, so let me bring up some of the first questions. So one of the queries that we have is about baseline numbers. So when it comes to what is an indication of a material being good or bad, is there some general industry standards and some baseline numbers that we can go off of? Maybe I can ask this to Professor Karen or to Martin.
Well, I think it's important to reiterate that it's not the material, but the way it's used. So, this is why you have to go to metrics like the CO2 per meter squared of building, because, well, concrete actually is a low intrinsic material, but it can be used both efficiently and inefficiently. So exactly the same material can have very different outcomes in the final buildings. And this is why we really need to go to these whole building metrics.
So now in terms of manufacturers, obviously a lot of this is going to be what the manufacturers are working on and what they're going to do within their processes. Now, we have a lot of developers and people working in the industry, but probably not a lot of manufacturers on this call. What can we do as our part of the industry to help the manufacturers know that we need to have them decarbonize? What kind of influence can the market do?
Yeah, now this is very interesting because this is a case of chicken and egg, and we have a lot of questions on this. I'm glad to say now that the industry is moving. We have considerable production now in Europe, particularly in France. There's a lot of new options coming available. And I think, we need to put users together with manufacturers. A good example of this is in India, where we've been working for a long time, and now they changed the standards. So, now we have opportunities to make demonstrations. So we're trying to, help in this process of putting things together. It's not always successful because, when you decide to build a plant making calcined clay, for example, it can take 1 or 2 years for this to come on stream, and people want it today. But we're doing our best here, but it's a challenge, and I think that the best we can do is that people make more and more clear that they are willing to use these low carbon products.
Okay, great. Now, another question around this kind of role of the designer, role of the people actually working in the construction of the buildings. How much, in terms of when we are designing the building based on the material choices, how much can a designer's choices potentially influence the outcome of embodied carbon? Obviously, this is quite a bit, but how should they approach these choices? Is one of the general questions.
Well, I mean, this is not my area. I'm not the total expert here, but I mean, many people have studied this, and this kind of savings possible at the design stage are even up to 50%. You can even cut in half the amount of material you need by a good design. So it's really, really enormous. I think it must not be underestimated. And, there are a lot of people really starting to work on this. I particularly mentioned my colleague, Dr. Dunant in University of Cambridge, who's working a lot on tools to help people design better. But I'm sure there are many others around the world. And, these are the kind of people you need to contact. But the savings really, really are huge. I mean, this is the main message.
And Irene, Ommid, yes.
Yeah.
Maybe I can just add to those remarks that in terms of the design element, one of the solutions that we provide is Edge. Within Edge, you can choose, and as Martin also mentioned, reducing the use of the material is the number one element, right? The number one element is not to use the material in the first place. Number two is, if you are using it, what can you do to reduce the use of that material? For example, in many buildings, we can get rid of finishes, not use the finishes. Or if you're using a specific wall or slab, you can reduce the quantity of material used within that slab or wall. And then number 3 is, while you have made everything to reduce the material, what are you going to choose? And the design of the building, of course, impacts those choices. And you can use EDGE as a design tool for choosing all these elements. It gives you the embodied carbon outcome, and that would be one of the ways to simply get to that answer if you're willing to do.
Now, I have a question, maybe directed more at Irene for this one, but when you are working with embodied carbon, what is the key difference that our EDGE experts and EDGE users are going to start to see in their results? Is it similar to what they would see before, or is it going to be very different?
Well, it will depend, but it's as Karen explained in a lot of detail, we are not talking about the same indicator. There is major differences. Embodied energy was not telling the whole picture, so now users will see a different. They still see the bars, but they will see a difference in their previous projects. Compared to results in previous projects, sorry. And this is why we always tell our users to look at the results bar, look at what are the low-hanging fruits. We try to make it as intuitive as possible in the app, as easy for everyone to understand. So there may be some differences, especially because now we have regionalized the data. Before it was global data. Embodied energy was a global indicator, now it's regional. So projects in Africa are not going to look the same as projects in Latin America or in Europe. So now obviously there will be a difference, but we believe this impact, this change has a great positive impact.
That's great. Thank you so much. Well, thank you so much. We're at the time, the end of our webinar today. I just want to thank our panelists so much, Dr. Martin, Professor Karen, for joining us. And we really hope that everyone has a chance. Again, it's edgebuildings.com. You can go on there on the upper right-hand side. You will see the EDGE application. Everybody is welcome. It's a free open tool. Create an account and explore it today. And I have also put in the chat, you have EDGE at EDGE at ifc.org. And that will be, if your question wasn't addressed, please feel free to send it directly to us. So again, thank you, everyone. Thank you to our panelists, and have a good day.
Thank you.
Thank you. Bye.
Bye.
Thank you.